The majority of scientists still firmly believe that the universe's origin theory provides the most compelling explanation for its beginnings. It includes the formation of planets, stars, and all life, including human life, on those worlds. The Big Bang provides a clear insight into what might have happened at the beginning, despite its unusual moniker. Particles were closely packed and the cosmos was once dense, condensed into a region smaller than the size of a pinhead. The Big Bang, an enormous burst of matter, originated from this tiny spot. This event, which took place billions of years ago, prepared the way for endless history to begin. But as science has progressed, there are more and more discrepancies between the predictions of the theory of the origin of things. The largest and most sophisticated space science observatory ever built, the James Webb Space Telescope, JWST, was launched by NASA with the expectation that its findings will support the notion of the primordial cosmic explosion. Regretfully, in its little time in orbit, the telescope has stunned scientists with its extraordinary ability to look back a very long time into the history of the universe. The astounding capabilities of the JWST have shown us worlds that date back to a time so far back that it calls into question our theory of the universe's origins. An extensive inquiry of the universe's pre-Big Bang state has been sparked by this discovery. An important turning point in this trip came when astronomer Rohan Nu, using data from the telescope, discovered by accident the earliest cosmos ever observed, a galaxy that dates back to a brief period of time after the Big Bang. This information shocked even conventional researchers and demonstrated the JWST's revolutionary potential. Its quest to transform our understanding of the cosmos is far from over, with the potential to unearth remarkable insights into the first stories of the universe's creation. Understanding the emergence of the first stars and galaxies requires an understanding of this remarkable, mainly uncharted era. The telescope's findings have upended long-held beliefs by exposing galaxies with properties that were not anticipated. Scientists are scrambling to fit these discoveries into pre-existing models as a result of the surprising quantity of early galaxies. Researchers now have important concerns about the underlying makeup of the cosmos and the forces guiding its evolution as they try to make sense of these disclosures. In addition, the JWST boasts cutting-edge technology. It is located 1.5 million kilometers from Earth, shielded from influence from the ground, and has a sunshield the size of a tennis field that keeps the temperature below zero. With its enormous segmented mirror and highly sensitive equipment, the telescope is able to show hitherto unseen details of the first light. A few 100 million years after the Big Bang, the first stars and galaxies formed during this era, which is referred to as the cosmic dawn. There is still much debate on how this happened, with theories focusing on everything from the interactions between starlight, gas, and dust to the impacts of dark matter and dark energy. Through the telescope's views of galaxies from the cosmic dawn, cosmologists have a rare chance to verify their theories about these important occurrences. Through the analysis of these old galaxies, scientists can either validate the accuracy of their existing models or point out areas of uncertainty that may provide important new findings. In its pilot trials, the telescope was initially expected to detect just a tiny number of faint galaxies, but these hopes were much exceeded by the actuality. When the telescope took its first images of the far-off universe, it discovered several worlds that were older, larger, and brighter than anyone could have imagined. A competition amongst space specialists to establish new records for the earliest known galaxies has been sparked by this unexpected profusion of early galaxies. Claims of yet another unprecedented discovery are made every day, stunning the scientific community and forcing a re-evaluation of our knowledge of cosmic history. Scholars and lay observers alike have been compelled to make sense of the existence of these unexpectedly found early galaxies since the JWST's observations. These unusual results have led some to hypothesize that errors in the telescope's first observation analysis could be to blame. All agree, though, that these findings give intriguing hints about the nature of cosmic evolution and mark a paradigm change in our knowledge of the early cosmos. The assumptions of conventional cosmological models are called into question by the latest JWST discoveries about early galaxies, which also pose important concerns about the nature of the cosmos. Some scientists wonder if these data can be explained by current ideas, while others suggest that they might be the first indications that the universe is even more unique and complicated than previously thought. Nothing less than our basic comprehension of how the cosmos came to be ordered from initial chaos is at stake in this question. JWST's early discoveries have the power to rewrite the first few pages of cosmic history, providing light on our own Milky Way galaxy's existence in addition to distant tails and faraway galaxies. In the words of European Space Agency Senior Consultant for Science and Inquiry Mark McCarran, "You build these machines not to confirm the worldview but to break it. You just don't know how it will break." Even before the Hubble Space Telescope was launched, in 1985, the Space Telescope Science Institute served as the genesis of JWST. G. Waite, the deputy director of SSI at the time, was assigned the responsibility of speculating on possible Hubble successors. Waite and a small team started building the foundation for what would eventually become the next-generation space telescope, which was later designated JWST, despite early misgivings. JWST can look even farther into the cosmos since it was built to see in the infrared spectrum, unlike Hubble, which exclusively observes visible light. This ability is essential for researching early galaxies, whose light has been bent into the infrared by the universe's expansion and is therefore invisible to Hubble-type telescopes. The largest instrument available for deciphering the mysteries of cosmic dawn is JWST, with its massive, icy mirror resembling a star. When the Hubble Deep Field Study in 1995 found a multitude of galaxies in what was previously believed to be an empty stretch of sky, it further highlighted the necessity for JWST. This finding demonstrated the richness of the early universe and reaffirmed the need for a telescope with the ability to go even further into the history of the cosmos. Ultimately deployed on Christmas Day of 2021, JWST cost over $10 billion and took more than 20 years to create. It was prepared to start its first year of scientific observations by July 2022. The goal of early initiatives like the GRISM Lens Amplified Survey from Space and the Cosmic Evolution Early Release Science Review was to look for early galaxies. Although there were low expectations at first, the outcomes were far better than expected. The observations made by JWST have revealed galaxies that contradict traditional theories, challenging preconceived notions about the early cosmos. These unexpected findings demonstrate the value of stretching the bounds of scientific inquiry and the remarkable potential of state-of-the-art innovations like the James Webb Space Telescope. Our knowledge of cosmic history and the forces that have fashioned our universe into what it is today is about to change as astronomers continue to solve the secrets of the cosmos. Space specialists were taken aback by the JWST's early surveys, which revealed incredibly distant galaxies considerably earlier than anticipated. Prior to JWST, GN Z11, discovered in 2015, was the most distant galaxy known to science. Its redshift of 11, which indicates a cosmic duration of almost 400 million years, made it such. But right from the beginning of JWST observations, the GLASS team, under the direction of Rohan New, and a separate team made a remarkable finding. At a redshift of 13, or roughly 70 million years earlier in cosmic history than GN Z11, they discovered a galaxy they named GLASS Z13. Improved methods for measuring redshift, which give a quick estimate of a galaxy's distance but are less accurate than direct measurements, allowed these discoveries to happen at a faster pace. Though far younger than the Milky Way, GLASS Z13 looked surprisingly bright and enormous, already with a stellar mass equivalent to billions of suns. Many galaxy candidates emerged with estimated redshifts as high as 20, indicating their existence just 180 million years after the Big Bang. More astounding findings were made during subsequent studies. It was unexpected for certain galaxies to exhibit intricate features at such an early stage in the history of the universe. Furthermore, evidence for Milky Way-sized galaxies emerged at a redshift of 10, which is less than 500 million years after the Big Bang. The mainstream cosmological model, Lambda CDM, which represents the evolution of the universe based on our understanding of dark energy and dark matter, is put to the test by these quick advancements. One major puzzle for cosmologists to address is how big galaxies formed in the early universe. Examining the initial moments of the universe's evolution following the Big Bang is crucial to comprehending this challenge. The earliest stars formed millions of years ago, when the cosmos was a hot, dense soup of primordial particles that would eventually give rise to galaxies. It is estimated that it took the cosmos roughly 1 billion years to undergo this enormous process of growth from its chaotic beginnings to the ordered universe we see today. This timeline is called into question by JWST data, which show galaxies that are too old for their cosmic age. Rather than witnessing the assembly of numerous tiny protogalactic components into larger galaxies, as suggested by existing models, JWST has discovered galaxies that are already massive and bright. By eliminating the potential of low redshift intruders, observations made with devices such as the Atacama Large Millimeter Array in Chile have added to the body of data indicating the existence of these far-off galaxies. These fundamental findings provide fresh perspectives on the early cosmos and might necessitate adjustments to our knowledge of cosmology as it exists today. JWST keeps upsetting our perceptions of cosmic history, testing our assumptions and expanding the boundaries of cosmological research. The lack of discernible dust in the Atacama Large Millimeter Array observations underscores the challenges encountered by telescopes when verifying JWST findings. As Rohan New pointed out, JWST's advanced capabilities enable it to cross-check its own observations, and ALMA's challenges in identifying the galaxy highlight how difficult it is to corroborate such findings. The observations made by JWST have important ramifications that could put the conventional LCDM cosmological model and requiring adjustments. The findings shocked Michael B. and Kulin, who proposed a significant divergence from what we already know about cosmology. Modified Newtonian dynamics, a contentious theory that casts doubt on the existence of dark matter and offers substitute explanations for the gravitational effects that have been observed, is one theory that might account for these results. Supporters like Mark McLo, who sees this as additional evidence supporting the concept, claim that JWST findings support this notion. Still, some experts, like Joss Arapi, are skeptical because they can't seem to reconcile MOND with the data that's available. However, the lack of dust in early galaxies may offer a more straightforward explanation for their luminosity, which could account for attempts to precisely determine their masses. According to Andrea Ferrara, dust might not have had enough time to form in the early universe or might have been eliminated during the birth of galaxies. Because they are simpler to view, Charlotte Artisan and her colleagues suggest that JWST may be detecting the brightest newborn galaxies. David Spergel hypothesizes that early magnetic fields may have played a role in initiating star formation and believes that the observed brightness of these galaxies could be explained by vigorous high-mass star formation in the early universe. This provides a possible explanation for the early universe's rapid galaxy formation. The speed at which scientific publications have been produced following JWST's initial observations highlights the significance of these findings and the profound effects they will have on our knowledge of cosmology. Researchers may find new discoveries that test and broaden our understanding of the universe as they continue to examine JWST data. Astronomers were excitedly anticipating the findings as the James Webb Space Telescope started to send back data. In anticipation, several had spent months refining their pipelines for data analysis. Space specialists published their findings far in advance of official peer review on AR14, a website that allows scientific papers to be uploaded with little to no scrutiny by mediators, rather than submitting them to the lengthy and regular peer review procedure, which can take months. This strategy made it possible for a brand new peer review process to emerge on social media sites like Twitter practically instantly. It's science by AR14, according to Rohan New, and the ensuing flurry of debate was furious and unexpected. The temporary director of SDSI, Nancy Levinson, acknowledges that she underestimated the scope of the work. Concerns exist, nevertheless, regarding possible drawbacks of this quick distribution of research. While rapid results sharing facilitates prompt publication and discussion, Klaus Horst, a JWST project researcher at SSAI, points out that there is a chance of hastening the process. He emphasizes the value of refereed, peer-reviewed studies as the ultimate standard. There have been identified early JWST calibration difficulties that could potentially impact some conclusions. Following recalibration, Nathan Adams of the University of Manchester and his colleagues discovered significant variations in redshift values for specific galaxies. These difficulties emphasize the necessity of prudence and in-depth research. Space specialists continue to be enthusiastic about the findings produced by JWST despite these challenges.